How you doing? Good. I'm pleased. Well, it looks like there's good people there. Yeah. That's wild. Yeah. Come on. Okay, let's get started. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker. But before I introduce today's speaker, there are a couple of students I want to recognize. Each year, our students compete for national awards and scholarships and fellowships. And we have a student with us today who won a fellowship award from the American Nuclear Society. And it is Thomas Miller, and he received a $3,000 cash award. He's already received the check, but we have a nice certificate for him here. Thomas, so come down here. As many of you know, our students are well trained in presenting papers and making oral presentations, and we've got good evidence of that today. One of our students presented a paper at the International Conference on Global Environment and Advanced Nuclear Power Plants, and he won the Outstanding Student Paper Award, and that's Martin Williamson, and he gets a nice certificate. So Martin, come down here. No check, that's right, no check. Okay, and now for today's speaker, who is Dr. Dave Hill, who is the Director of the Nuclear Science and Technology Division of the Oak Ridge National Laboratory. Dave received a PhD in mathematical physics in 1973 from the Imperial College of London, and then he received an MBA from the University of Chicago in 1995. He worked for several years in Great Britain for the United Kingdom Atomic Energy Authority, and then in 1984 he joined the Argonne National Laboratory, and he rose through the ranks and eventually became the Deputy Associate Laboratory Director at Argonne. In 1984, he was there from 84 until 2002, and then in 2002 he came south to the Oak Ridge National Laboratory in the position that he now holds. The topic of his presentation today is the future of nuclear power in the United States with and without closed fuel cycles. Ladies and gentlemen, welcome Dr. Hill.
Thank you very much, Lee. I'm going to do the mea culpa right at the beginning. What you're going to see is my views. I'm going to be talking through here about what DOE says it does, what the administration says it does, and my interpretations alone shouldn't be treated entirely as gospel. And I'll also apologize for I'm inevitably going to make a mistake with this thing, because my style of giving a talk, as you can probably tell already, is to move around and point a lot. I've been told to stand on a dirty brown mark. And so this is roughly I do that already. I'm going to talk about how this administration entered in 2001 and the policies they adopted, how they match up with the DOE programs. The 6 national labs got together and have been pushing a strongly pro-nuclear agenda. I'll discuss that a little. Some international views. Very recently, John Deutsch and Ernie Moniz, John Deutsch, former director of CIA and I don't know what he was, Deputy Secretary of Energy at some point, and Ernie Undersecretary of Energy at some point, were both MIT professors, led an 18-month study with Sloan Foundation money on the future of nuclear power. I'll discuss very briefly their conclusions and some of the responses to that, and then back it up with some opinions of my own. Starting to move already.
That's okay.
This administration came in believing that energy was crucial to the future of America. And in the National Energy Policy document, which you've read a lot about, how did I do that? Put a case for not only developing nuclear power, but for reopening discussion on reprocessing and scientific work. Reprocessing in this country has been almost a taboo word for 25 years. Very soon after that, because of strongly geopolitical desires to have a rapprochement with Russia,
It hasn't mine.
clearly.
It does. It's common.
Yeah. As part of the preamble to the Bush-Putin summit in '02, I'll give you more detail later, but nuclear power and nuclear cooperation with Russia entered the presidential arena. And as far as this administration is concerned, the four issues, the classic four issues, can be prioritized in this way. Solving the waste problem. They aggressively went after dealing with Yucca Mountain. Economics. This is a Republican administration. If you can't make nuclear power economic, it's not going to fly, no matter how much you want it to. Non-proliferation. The issue of proliferation of weapons material and safety of all the four issues is least concern there. Now, for those of us who work in the DOE world, you recognize that administrations come in and say one thing, but the DOE bureaucracy is a ship that's slow to turn. And there are existing DOE programs prior to that get modified by administration positions, but only very slowly. If I can ever find this pointer, there it is. One of the programs, as far as I'm concerned, one of the most interesting programs is the Advanced Fuel Cycle Initiative, which is what we ended up naming the reintroduction of reprocessing in this country. But prior to fiscal year 2003, the administration, including the Republican administration, including an administration that supported it in the National Energy Policy document, put zero budget requests for it. And the flagship program, Generation 4, had less than $10 million. So it was really a paper study. I have no idea what's happening here. At the higher level, in the strategic plan, there's still strong support. They want to build a new commercial reactor by 2010, and they want to build a Generation 4 reactor by 2020. So, what is the Generation 4 program? I'm going to give you this very briefly. This was held over from the late 1990s. It was DOE-led international program to select the next generation of nuclear technology. They were looking out 2030 beyond, not immediate. So it was meant to be research. And the criteria used were, again, the usual ones: non-proliferation, safety, economics, but sustainability. Sustainability meaning efficient use of resource, energy for the long term. And out of that exercise, which was somewhat a 2-year exercise involving hundreds of nuclear professionals from this country and around the world, there were 6 basic concepts selected. And this is the one that's getting the most attention now. VHTR stands for Very High Temperature Reactor. The idea of taking a gas reactor and seeing how high you can push it in temperature to get the benefits of gas turbine technology and potentially hydrogen production. Over on there is the supercritical water reactor, which is actually misspelled there. This is taking water reactor technology, pushing it up to use supercritical water and seeing how far you can push water reactor technology. I can't use this. There it is. The 6th one was the molten salt reactor. Oak Ridge's past, and that is a molten salt reactor. That's salt, fuel in salt, dissolved process with online reprocessing. The other 3, the gas fast reactor, the sodium fast reactor, and the lead fast reactor. Now, I'll give you my interpretation of this 6. You have high temperatures for hydrogen. The 3 fast reactors all appear because of the sustainability criteria. In the end, if you need to have large amounts of nuclear, you've got to deal with the back-end material. You have no reliability of the supplies of uranium, and it forces you to a closed fuel cycle, and they're all aspects of closed fuel, which forces you to fast neutrons, which forces you to a closed fuel cycle. So this exercise which for the older people in the room will recognize is probably replaying 50 years ago history, but was what people fail to understand was it's more important for the process than it was for the product. Because a whole generation of nuclear engineers were forced to face up to the fact that if you really had to think about the future and large-scale use of nuclear energy, you had to think about fast neutrons at some point. You have no choice. Now, the Advanced Fuel Cycle Initiative in 2003 was set up with so-called two series, Series 1, Series 2, imagine to be named. The Series 1, the idea behind that is to use existing technology, existing LWRs, and to see what could be done quickly and therefore cheaply. Series 2, somebody else got one, please. Series 2 is the fuel cycle that goes with those reactors, the Generation 4 fuel cycle, the closed reprocessing. It's being slightly recast this year. Every year it's recast, but the new and correct focus is this thing. We've gone through the exercise of getting Yucca Mountain one step forward, but written into the law is the requirement for the government to take a decision on the second repository. We didn't know there was going to be a second. There's going to be a second repository, and the law is such that it has to be taken somewhere between 2007 and 2009. Now, reprocessing or processing or recycling offers, at least in principle, a means of avoiding a second repository. And there's a lot of benefit for the government in that, at least politically, because, again, on repository, one of the problems with repository is it's in Nevada in the west, and most of the nuclear plants are in the east. And Westerners see this as a shift of radioactive waste from the east, who get benefits from the power, to the west, who just get the waste. The other thing about advanced fuel cycle, and
Maybe put it down.
I'm going to go back to tapping, okay?
And just double fit.
And probably still do it on its own. But the other thing about the fuel cycle that's interesting, I told you beforehand that prior to 2003 there were no budget requests, but I think it was 2003, 2004, I've lost my years now, but the most recent budget request was the first time that DOE had actually, the administration had requested money for the fuel cycle work. There was a request for about $50 million. It had taken those of us who worked on it 5 years to get to that point, and I was one of those. But that, as far as I'm concerned, is a signal achievement. This country now officially appropriates money to do R&D on reprocessing. Okay? Remember that. That's much easier. So, what we're doing right now in this country, of course, is the once-through fuel cycle. We just irradiate fuel and put it in the ground. The two possible alternatives are a so-called single-tier transmutation system. Don't worry about too much of the words. All that means is the classic of taking spent fuel, processing it, and putting it in a fast reactor, or just possibly an accelerator-driven system. I don't propose to discuss accelerator-driven systems here, but this dual tier, at least as drawn here, has a single pass of MOX and LWRs before moving to a fast neutron system. DOE put together a program where this is integrated, Gen 4 and AFCI, and you can see, and I assume you have access to the view graphs afterwards, that there are many working groups set up dealing with not only the classical nuclear problems, but problems of hydrogen, different thermochemical cycles, desal, process heat, and so on and so forth. Now, so, the administration is pro-nuclear, but is short of money. It's got to pay for wars and other things. DOE, the Office of Nuclear Energy, is an underfunded office and has been growing a program and doing an amazing job of it, but it's growing slowly. So, one other thing we were able to achieve was to get 6 national labs, the directors, on a common push, and it really actually represented 8 labs because Oak Ridge is operated by Battelle, and the 6 did not include the other 2 nuclear Battelle labs, Brookhaven and Pacific Northwest. We took care of that business. So we had the 3 weapons labs, Los Alamos, Livermore, and Sandia, Oak Ridge, Argonne, I've forgotten somebody. Who have I forgotten? Idaho, yeah. How could I forget?
Freudian slip, that's what that is.
Yeah. As I said, the 6 labs. And the next set of view graphs are a presentation describing that effort. I will skim it lightly, and if you have more interest, look at the view graphs. But there were a set of recommendations made to the Secretary. Now, this is a parallel effort. This is not a funded effort. This is getting 6 labs to agree on pushing an agenda pro-nuclear. I'm sure the people here who've worked in national labs understand what a momentous task that is. I mean, it is amazing that we could get them to sign on anything. And to have such a strongly pro-nuclear agenda, nuclear, civil nuclear, and include the 3 weapons labs is really, I think, again, another signal achievement. It proposed a program of about $1 billion over 5 years. It's been briefed all the way up to the Vice President, and Secretary Abraham and Deputy Secretary McSlarrow asked us to develop an action plan. At the same time, this was the time of the Bush-Putin summit. This is a direct quote from, I think, the communique. And what they formed after the summit was a working group to explore cooperation in reactors and fuel cycle. I was part of the DOE team to do that, although I'm not a DOE employee. I had worked on a previous negotiation with Russia in 2000 on a very similar thing, so I went along, and twice we wrote a report saying cooperation with Russia would be good, and here are the topics, including fast reactors, gas reactors, different forms of processing. And twice it failed because the U.S. and Russia decided to disagree over Iran and Iraq and other issues. I've told Magwood I'll do it one more time, and then if somebody else can have a go. But it's exactly these elements that bring the weapons labs to the table, because they believe very strongly that it is not a viable future for ever-increasing amounts of weapons-grade material in separated or easily separable form to exist. And they want to tie it up. Their non-proliferation experts believe the best thing you can do that is tie it up in the fuel cycle. And that's the commonality that brings the weapons labs and the non-proliferation experts together with the nuclear power people. So in the 6 lab agenda, there were 3 goals. These are very high-level goals, and there are documents on this that I can transmit. Reduce air pollution, this is the CO2 goal. Try and limit ourselves to 1 repository, 90% reduction in waste, and control nuclear material. And this steps out an action plan, and unfortunately light isn't, that's not a great view graph, is it? But there is emphasis there on early construction of a new plant, commercial, building a demonstration plant by about 2020 for hydrogen production, again, probably tying to the VHTR. If that indeed is the way to make hydrogen, I have my own opinions on that, but however it's done, that is not a resolved issue yet as far as I'm concerned. And getting to a fast cycle reprocessing demonstration for the purpose of controlling nuclear material, limiting the production of weapons grade. And that's the proliferation risk part of this. The next few view graphs go through this in detail, and I'm not going to discuss them. The words, again, I'm assuming you can have access to the view graphs. But this is the picture that this, with much trepidation, this is the picture that we saw in this group. You have the existing fleet of reactors, which at their nominal retirement dates would give you a nuclear power historical profile like that. If you add on everything relicensed, that, and power up rating, still by 2030 things start to decline. If you imagine a replacement fleet of advanced LWRs, you start building them now, so there's a bump, but in the end, here you've only added another 100 gig, and they have longer lifetimes, they'll go away. And that is not going to do it with respect to CO2, that is not going to do it with respect to the energy needs. I have no idea what I'm doing. we're going to meet the anticipated energy demand and affect the CO2 emissions that come from the transportation sector. Remember, direct production of electricity is only a third of the emissions in this country. It's roughly a third energy, a third transportation, and a third general building heat and the like. So, it must be the way I wave my left hand or something. If you're going to make an impact on CO2, you have to get into the transportation sector, which means hydrogen, either direct use of hydrogen or hydrogenated fuels. And if you make the hydrogen by fossil, all you're doing is shifting your emissions from one place to another. So nuclear, at least in principle, has a part to play in the solving the transportation dilemma. So that's a list. There was a letter that was sent to the Secretary. I can't get this thing to work. There it is. Again, signed by the 6 lab directors, which detail that. Nuclear waste is key. And this 6 lab group believe that closing the fuel cycle ultimately is essential for the long-term use of nuclear power. Ultimately is a debatable word. Whether that's 10 years or 50 years remains to be seen, dependent on real-time growth rates and economics, but ultimately needs to be done. And there are 2 strong reasons. The actual management of the waste, reducing the inventories, getting the actinides out of it, which will in turn will reduce the radiotoxicity. And later on, when I come to some of the international positions, I think you need to focus again on this business of leaving actinides in waste or getting them out. And from a proliferation point of view, actually managing the materials. Managing nuclear material is crucially important. Here. I wasn't even touching it there. We've seen that one before, so let's get. Now, if we're able, this is a impact of recycle figure, which goes with the first figure with the introduction of fast reactors. And this is the inventory in metric tons of heavy metal of waste that would go to repositories. And this green line is the path we're on now. The capacity of Yucca Mountain is 70,000. 70,000. So the first thing you need to know about Yucca Mountain is that it's full about here. And most of that fuel has already been discharged from reactors already and is sitting in ponds. Okay? So Yucca Mountain is full. Now, it turns out the geology of Yucca Mountain is such that if you could convince the state of Nevada to do it, you could double or even triple the effective usage because there's the way the fracture lines run, etc. So you can imagine. Where are we? Here we go. You can imagine Yucca Mountain probably reasonably taking about that much fuel. But if you can introduce fast reactors, either direct, so-called, the first of the schemes or the second scheme with a MOX pass, you can limit the requirements on a repository to take spent fuel. So in principle, nothing here about whether it's economically possible or technically possible, but in principle, you can limit this country's need for repository at the same time as having the energy you need and the carbon-free energy. So the question is, what do we have to do to get there? And I won't do it when I ask you to. There we go. And expressed as toxicity, ratio to the toxicity of natural uranium ore, this is pretty much a classic picture now. It takes you 10,000 years, 100,000 years for spent fuel to get down to that level. If you pull the actinides out, and all you're doing here is taking the actinides out and leaving a little bit in, on order of less than 1,000 years, you're down at toxicity, human toxicity, at essentially the same as natural uranium ore. Now, I've read the technical cases for Yucca Mountain. They're brilliant engineering arguments, but there's some things about it bother me. For example, you assume the hydrology and the geology and the population is essentially the same for the whole life of the repository, which is 10,000 or 100,000 years. Because what else are you going to assume? Now, I haven't checked the data on magnetic field reversals and ocean current reversals and everything else, but I'm willing to bet that it's not as predictable as that within that time. And I think people, the man in the street, understands intuitively that at 1,000 years, engineering structures can survive. The Sphinx, the pyramids. Nobody, I think, intuitively believes engineering structures are going to run you out to 100,000 years. It's just unimaginable. And I think that's one of the origins of the people, the general populace's concern with storing waste for that long. Even though the hazard implicit in the waste for much of that time is very, very small by any rational standard, to people, they would much prefer to see a picture like this. And this comes again to where the French have their views. Again, the Sixth Lab group emphasized economics. You can do all of these things in principle. If you can't make it economic, it's not going to work. And we're going to have to expect fusion or directed solar energy or something is going to take the place. Proliferation. Controlling and managing nuclear material is essential. And I think the events of the last 3 years, although the attack in September 11, 2001 was with an unconventional, conventional weapon, and basically an airplane as a missile, there have been enough examples, or if you read your press, enough examples or concerns about the trade and traffic in nuclear material for this to be a very serious concern for our security folks. And unless you have to imagine for the future a nuclear enterprise that controls nuclear material. I'm going to skip these. That's just detail. But these are some of the things that we were proposing should be worked on as part of this, looking at advanced technology requirements, simpler reactors, maybe even sealed core reactors. The idea there being you take a almost like a nuclear battery, is one thing we call it. You ship it, place it, you attach it to the grids, you generate electricity, it's designed so it has a 15, 30-year core life. You come back, take it back to the originating country, presumably the U.S. or somebody you trust, Russia. That's interesting. Russia and trust in the same sentence. And replace it. In other words, you keep the reprocessing and dealing with nuclear material in countries that have the expertise and social stability to do it, and you get the electricity to where it's needed. Because all of the electricity growth in the next 50 years are going to be in places like Indonesia, Sudan, Ethiopia. The electricity growth is relatively modest in global terms in this country, a steady few percent a year. With the explosive growth of population, raising living standards in the poorer part of the world, which is the essential requirement to making the world a safer place, will mean that the energy requirements in the other parts of the world is going to be massive. And the only thing on the horizon that can do that is nuclear, without damaging the environment, yet we have the nuclear material problem. Advanced reactors and so on and so forth, limiting enrichment. So, as a Sixth Lab group, I was originally Argonne's representative on that group. When I moved to Oak Ridge, with Gordon Michael's work, the Oak Ridge side of this. In fact, myself and a guy from Los Alamos basically put this whole thing together. Provide the incentives to get a near-term build. We need to be building in this country. Demonstrate advanced systems. Demonstrate the closed fuel cycle, and show the world the technology, satellite-based technology, material tracking technology, which gives people the confidence to believe we can go forward in nuclear energy without being concerned about proliferation. And I haven't mentioned on the way through, but an important codicil to our whole arguments were, if you imagine a nuclear future, what's interesting, there's sort of age stratification going on here. Let's have a down the front. I think the first two rows of me, I must be average age of some large number. And folks will be back, and I'll put David and Valmore in that, a much smaller number. And without you guys at the back, none of this is going to happen. because I'm going to be gone, and these guys are going to be gone. So we, in the lab system, believe that the government needs to focus very heavily on university nuclear education, providing R&D at the labs and the universities that excites the students and brings them in and develops the technology. And this one, we have to find some way of rationally remembering what everybody down at the front here knows and passing it on to you guys. No disrespect to a university. You get the basis of the university, but you really learn by doing it and working with the people. So there has to be an information transfer by placing university students in co-op programs, PhD programs, working with the other ones to get this done. And that's moved on without me, haven't I? The other way. So, this is my opinion. They ask me what's the future for nuclear energy in this country. I get asked that a lot. And this is British understatement. There is cause for optimism, but it's scarcely unbridled optimism. But there's genuine cause. And why do I say that? Well, you only have to look back 5 years. In the last 5 years, we have put together, albeit only a fledgling, but an international advanced nuclear program, Gen 4 program. Reprocessing was explicitly called out in the administration's National Energy Policy document, and we have funds appropriated to do research on reprocessing it. It's small and it's nowhere near what's required, but it's on the table. And anybody who's looked at negotiating theory and framing, there's a whole lot of difference of having zero budget and arguing whether something should exist, or having something that exists and then just arguing about what level it should exist. So that was the big barrier. And furthermore, the dialogue with Russia as well as our traditional partners has started. It's hiccuped again, but by the end of this decade, we will be doing active, cooperative nuclear R&D with Russia. Let me turn now to things I know less about. What is the U.S. industry view of this? And those of us who live in the national lab world usually say U.S. industry, but of course it's got subcomponents that don't always agree with each other. Vendors, needless to say, want to build reactors because they want to make money. So everything they do is focus on that first element, which is getting a reactor constructed by 2010. And in fact, have been known to criticize some of the R&D programs as deflecting from this all-important desire to get a reactor built. Needless to say, I don't agree with that, and I think that's extremely short-sighted of them. Utilities, on the other hand, in the old days of regulation, used to have a vested interest in nuclear research and nuclear development, but after deregulation, they became, frankly, just like any other company, they make a product. That product is electricity, which they sell for money, and they have no vested interest in any one technology. It's purely a market decision. And therefore, it's difficult to get their attention. The only thing that might get their attention is hydrogen. There's a very large hydrogen business in this country already, which you may or may not be aware. Hydrogen is wheeled all around places like South Texas. It's used in chemical refining, hydrogenating heavy oils. So commercially, there's a big hydrogen business already. And you can imagine building reactors for the purpose of feeding hydrogen. I can imagine it. I don't think it's likely yet, but it's imaginable at this point. So from an industry point of view, very short-term, modern market economics are really a barrier right now. What is the international view of this? France has over 80% of its electricity from nuclear power. It's actually not the answer to the trivia question, which country has the highest fraction of nuclear electricity? Then we know the answer to that.
Lithuania.
Bingo. Lithuania is the highest. It actually, in principle, has over 100%. And that is because when the Soviet Union broke up, the two large RBMK units, which were built to power eastern Russia, ended up in Lithuania, and the output of those two reactors far exceeds Lithuania's ability to use electricity, which is fine because the transmission lines all point back to Russia. France, 80%. It's already actively reprocessing using Purex, aqueous chemistry, standard processing. They also recognize the concern on plutonium, and they have a program which is designed to produce different assembly designs with partial burn in them, and the goal being to cap their inventory of separated plutonium. So they'll separate plutonium, but put it back in MOX, and so they don't have an ever-increasing stockpile of separated weapons-grade plutonium. In 1991, they passed the management called Law of 1991, which authorized a 15-year program to investigate alternatives to the repository. Waste is a very big issue in France, but they also recognized for geological and social reasons they couldn't figure out if they'd ever be able to build a repository. So they put a very large R&D program in place to investigate that. That will report out in 2 or 3 years' time, and it'll probably say we know enough to continue to do more research on this. And that's where things like this program come from. And most recently, 2 French congressmen, I don't know the term, did about a 6-month study and produced a report to the Congress. It's freely available, and it has an English summary, which basically supported the French position on R&D in the nuclear arena, including high-temperature molten salt cooled reactors, not fueled reactors, including the French position on fast reactors. There's political reasons why they did that. We won't worry about that. Russia, on the other hand, is committed to nuclear power and recycling. It has been for its whole career. Russia invested an enormous part of whatever wealth it created in its nuclear complex for the production of weapons and weapons material for the arms race. It has a very large nuclear complex that it needs to support. It can't afford for these people to be unemployed because they'll go places where they can find employment where we probably wouldn't like. So it's a very large infrastructure. It's just not politically possible for Russia to walk away from nuclear even if they chose to. However, what they've done, their policy, Russia is one of the largest resources of hydrocarbons there is, and they continue to find more. And because of the geopolitics, what they want to do is export the hydrocarbons, pipelines to Europe of gas and so on and forth, get dollars, because they've got the infrastructure support. They're going to invest in nuclear to keep their nuclear business together, produce nuclear electricity for domestic use to free the hydrocarbons for export. So in Russian economic terms, political terms, that makes the most sense. And they believe, for the same reasons that the Generation 4 forum came out and said for sustainability you need to have fast reactors at some point in the future, they believe in fast reactors and are eagerly seeking fast reactor cooperation with the West. A little side note, should have mentioned it earlier when I was talking about the cooperation with Russia. About this time last year, when we were still thinking we might get something going with Russia, Condoleezza Rice, you've heard of her, was actually interviewed in the Financial Times of London, and one of the things she said was supporting the Russian fast reactor program, arguing that the US should get involved in it. Japan has no feasible repository site and no hydrocarbons. Tough spot. And until recently, we're very, very strongly committed to nuclear power and recycling for the reasons we've already discussed. And I believe we'll remain committed. Of course, you've all read in the various scandals associated with the Japanese nuclear industry, Takamura, concealment of problems at the power plants, and so on and so forth. That'll make it difficult in the short term, but in the end, Japan has no choice. It's an industrial company that has to have energy. It can import hydrocarbons, but it will be held hostage. And most of these countries see that what I call energy security is crucial. We have the luxury in this country of having a vast array of energy available to us, if I include Canada and the tar sands, that it makes decisions easy for us to put off. If you're in Japan, France, you have no choice. You either go nuclear or you import hydrocarbons and put yourself at the mercy of the petroleum exporting countries. Change of pace. About 18 months ago, Ernie Moniz, who used to be Undersecretary of Energy in the last administration and went back to his job at MIT as a physics professor, and John Deutsch, who is Professor of Chemistry at MIT, and a previous Democratic appointee as various things like head of CIA, Deputy Secretary of Energy, I think even maybe Deputy Secretary of Defense. Very, very politically connected people. Ernie had to deal with the nuclear power issue when he was at DOE, and was frustrated that he didn't feel he was getting a clear and coherent picture from the labs or from his staff. I can understand if I weren't from that. Managed to convince the Sloan Foundation to finance a study. This is on the web. You can get this. It's very, very good reading. You need to, in my opinion, again, my opinion, this should be seen as prototypic democratic policy for if they win an election. These are two democratic political appointees. It's not unreasonable not to expect that. But I've taken the liberty of summarizing a 200-page report in 6 bullets. So if Ernie is watching, I'm sorry. But I actually really think this is a very good report. I disagree with it on one essential conclusion and some of the facts that led them to the conclusion. They said, first off, it also had people like John Holdren, who is, not what he is, but he's another MIT professor and chair of PCAST, President's Commission of Advisors on Science and Technology, and a heavy environmentalist of the most virulent sort. But even John Holdren has arrived at the position that maybe CO2, the problems associated with global warming are worse than the problems associated with nuclear power. So, if you start from the premise that you need to make a difference in CO2, and you need an energy mix, which I agree with, and you end up by figuring out a very simple calculation with nominal growth rates, you need 1,500 gigawatts nuclear just to maintain market share, 20%, or whatever it is nationwide. That's a lot of nuclear power. 1,500 gigawatts. And where's it going to be? If you homogenize it, it's going to be in Ethiopia or Indonesia. Well, probably not, but there'll be some heterogeneity. But in general, it has to be a form that can be used worldwide. They concluded that the current nuclear architecture, by that they mean light water reactors and sticking the waste in the ground, is fundamentally flawed and needs rethinking. But they don't accept the premise that you need advanced fuel cycles now. They say you've got 50 years to worry about it. I'm not quite sure how you close the circuit there, but that's what I said. That's how I read their report. But clearly, if you do this, interim storage is required. You don't need to put everything in the ground for 100,000 years. You can build storage, just subsurface storage. They strongly recommend looking at other forms of geologic disposal, including deep boreholes. I have an opinion on that, which I'll leave. They conclude that the once-through fuel cycle is, cheaper and safer, arguing that the frequency of fuel cycle accidents is sufficiently large to be a concern. Now, they came to these conclusions because they did a study which told them that basically there was very much larger supplies of uranium than was commonly given credit for, and that there was no need from a resource utilization point of view to go back to recycle. So they said, okay. And then they said, well, proliferation is such a large concern and fuel cycle and reprocessing encourages proliferation that we don't want to do that. And that led them to this position. And therefore they said this country should not be pursuing fuel cycle research. I think their data on uranium is speculative at best. I believe that certainly we don't need to build fast reactors tomorrow, but what I do believe is different then is I think we need an active research program on fast reactor plus recycle, and in more in general, the nuclear architecture, looking for systems of combined OWRs, fast reactors, and it usually comes out as an 80-20 roughly ratio, symbiotic cycle, we've called it, where you have a few fast reactors burning the waste from thermal reactors, and we can't afford to wait from that. I mean, the government should be in the business of providing technology options for policymakers, and I don't view an option to say, you've got 50 years, don't worry about it. However, it's a very good report and you should read it. This is primarily the French response to that in a formal document transmitted at least to individuals in the country. I have a copy. Same as me, they're not optimistic on uranium supply, but they do certainly support an international assessment, which was something that the MIT report proposed. They commented that the economics, Ernie and John said, well, they went through a simple economic model and demonstrated to their satisfaction that nuclear wasn't economic right now and require substantial improvements in capital cost, etc., to make it economic. Their comment was they've done their own studies in France. Nuclear power is economic. Hydrocarbons have to be imported and so on, so that the economics are different in the US and Europe, and maybe the MIT economics was pessimistic. They said explicitly that the MIT report has the back-end cost wrong. The French have had a study in 1999, including the Chopin report, which showed to their satisfaction. I say that because I haven't personally gone through this report, and can't, but their claim is in there that if you include the sunk cost in La Hague, that the cost of reprocessing is basically 10% of the cost of electricity a cent. If you discount La Hague as sunk cost, it's 2%. Now, why would a country like France pay that? Even recognize whether you agree the actual number would play a premium for reprocessing? Well, 3 reasons. One, at least originally they wanted plutonium. They don't want it anymore. Secondly, they do not believe. Secondly, of course, they need the nuclear power. They don't have a choice. And the third and most crucial reason is they believe socially in France you will never be able to put nuclear waste in the ground containing plutonium and other actinides. It's not a technical argument. It's purely a social argument. They still literally think it's impossible. So they feel they have no choice but to pursue a path where the actinides are eliminated from the waste. Now, if you take them from the waste, what are you going to do? Collect them in little pots? Well, you're essentially accumulating weapons material in one place. You try and destroy them. And how do you destroy them? You destroy them with fast neutrons. And they also say that the deep borehole is a non-starter. And that is the general consensus, at least of previous studies of deep boreholes, because simply you're dominated by uncertainty. You don't know what's going on down there, and nobody can imagine dropping this stuff into the center of the Earth without any predictability. So everybody who's looked at this has come to the conclusion that there's nothing a priori wrong with it, except you really don't know what's going to happen to it, and that's not a good way to handle nuclear material. And they also say that experience in France and the UK is that reprocessing is demonstrably safe, and that the MIT report has overstated the problems with reprocessing. Okay, now me. How are we doing on time?
You're doing fine.
This is what I think the future holds for us. I think we'll continue to see advanced reactor and fuel cycle R&D in this country. It will increase, not dramatically, but steadily. For different reasons, we'll see increasing cooperation with traditional partners, France, UK, but Russia. Russia is so important geopolitically and has such a large nuclear infrastructure and will continue to invest so much in nuclear, this country cannot afford but to engage with it for simple geopolitical reasons. And that is actually this country, in that we'll be able to cross-fertilize technologies and possibly even see a fusion ITER-like project. I can imagine, I'm not saying it's likely, but I can imagine by 2020 that Russia, US, France, Japan are cooperating on the construction of a next-generation simple fast reactor somewhere in Russia. In this country, we'll see increasing focus on the second repository decision. As Yucca Mountain becomes more and more inevitable, we have this next political bombshell waiting, which is the administration has to commit to a second repository, and I think the drop-dead time for that is 2009. And the interesting thing about the dates 2007 and 2009 is, between it is an election. Now, the game is who gets to make the decision. If it's a decision you don't want to make, you leave it for the next guy. If it's a decision you want to make, you take it. So I can't predict how this will turn out, but I can tell you there'll be plenty of focus on it. This country has held a policy for a very long time that there should be no accumulation of separated plutonium. Separated plutonium. By that I mean pulled away and separated in essentially immediately weapons usable form. That will remain. This it was introduced effectively by Carter, reaffirmed by Clinton in PDD-13, and this administration, National Energy Policy, also reaffirmed that. So you'll see a force towards processing that does not give you separation of plutonium. I mean, even the French going that way by using these fancy assemblies which cap the amount of plutonium they have in inventory. This country places negative value on plutonium. France, positive value, and I was just talking to the British last week, and they decided plutonium has zero value. Not negative, that's good.
Russia's positive.
Russia's very positive, yeah. We'll see more work on repository science, geological isolation. We'll see work on things like deep boreholes. We'll see work on interim storage. If you think about how nuclear energy will develop in a social, economic, market way, it's very difficult sometimes to see how these things will get built. But as they do, the government owns the waste, and the government takes responsibility for it. That was the essential trick of the Nuclear Waste Policy Act, making that clear, separating the responsibility from the people who generate electricity for a small fee. So I expect to see more of that stuff. And personally, we need, I was being facetious here, we need a grown-up attitude to the fuel cycle in this country. Since the Carter years, we've been doing this. Other countries have moved on, and it's a very, very political subject. What we've achieved over the last 5 years, and a large number of people working, is started to create what I think is the basis for a legitimate debate on the future of nuclear power. And going back to the MIT report, 5 years ago, I can't have imagined a group of people, including Holdren and Deutsch and Moniz, and people who are from that political grouping, even deigning to do a report. And this was a serious report. It wasn't, it had very, very good academic credentials, and it's a very, very good report. And its simple existence, the fact that a group of people like this are turning their attention to that subject, I think says volumes in itself. You may not agree with all the conclusions, that's your option, read it for yourself. But remember, the fact that it exists is important too. All right, I work at Oak Ridge National Lab, in case you hadn't noticed. So what is Oak Ridge going to do in this respect? We were commenting beforehand, there are other labs that are focused on advanced reactors. Oak Ridge was traditionally a home of a lot of the reprocessing work, but when the government gradually got out of the reprocessing business, that work went away and the people have moved on to other subjects. But Oak Ridge has a lot of core capabilities that are immediately applicable in this world, the world I describe. Gas-cooled reactors is a core capability, in particular the fuel for gas-cooled reactors, particle fuel. Basically, Oak Ridge is the keeper of the technology and the developer of technology. In the government sector, we know more about the economics of nuclear power than anybody else. In fact, very few people know about the economics of nuclear power. Because of our work with Russia on the fissile material disposition program, we know more about MOX than anybody else in this country, a lot more. Bella here and others know I&C, instrumentation control, diagnostics is a core competency. And in fact, in general, most things to do with thermal reactors are an expertise at Oak Ridge. Both materials, which doesn't lie in my division, materials is a major expertise at Oak Ridge, but material processing, we've kept the technology alive, coated particle technology, molten salts, David, aqueous reprocessing, doing a lot of these, using a lot of these technologies in other contexts. And all of this is applicable to the advanced high temperature reactor. What's the AHTR? This is the only new thing that came out of the Generation 4 process. The 6 identified concepts are really all modifications or well-known systems. I'm sure the front 2 rows recognize all of those reactors. This was a genuinely new idea. And I'll tell you what it is first, and I'll tell you why it is. It is simply a gas reactor, carbon carbon graphite compacts with particle fuel, but not cooled by gas, but cooled by molten salts. And why would you do that? Why would you do that? To make a gas reactor requires you operate at pressure. If you go into high temperatures, you want to make hydrogen. Start with a hydrogen plant. That's ambient pressure. So it means you're going to transfer very high temperature heat. Oh, by the way, because of nuclear safety regulations, this hydrogen plant has well outside the emergency planning zone, or whatever zone is the right zone. I don't know my NRC language, but it has to be quite some distance away. So you've got a long distance, you've got a lot of heat, and you've got to wheel that heat. And you have a pressure difference as well to get over if you use gas. Now, if you use a molten salt, a liquid, which can cool the reactor at ambient pressure, you immediately take out a whole class of material problems, because then you don't have any delta P over the heat exchangers. Secondly, what does the chemical industry, what are one of the fluids the chemical industry use to wheel heat? It doesn't use gas. It uses molten salts. So it turns out that this is a sort of marriage of a number of concepts. If I were to squint, that reactor looks like a simple pot-style fast reactor, except instead of simple sodium or something in there, and a molten salt. It has the gas reactor fuel technology, and it has a number of benefits that come to that. For the same size vessel, which is one of the determining factors of cost, the specific power density is very much higher. And the safety case, which limits the power of the reactor, usually for a given vessel size, will limit a gas reactor to, say, 600 megawatts. We think we can get a molten salt cooled equivalent up to 2,000 megawatts. Because if you have gas, your conduction limited. To get the heat out in an accident, you have to send up the temperature gradient, and the heat has to flow down it. With the liquid, you get convection, and if you have a high heat capacity liquid, the temperature rise is small. So this turns out to be, I haven't got the full discussion here, but it turns out to be a concept, and it's only a concept at this point, that is pretty much optimized for high temperature hydrogen production. Because you don't have the delta P problem, you can go to bigger sizes, therefore cheaper per unit megawatt in principle again, you'd have to do the studies. And there are no obvious drawbacks. The industry knows how to run molten salts. So, that's an Oak Ridge concept, which we are trying to persuade DOE to fund right now. People working on it are people like Charles Forsberg. We're doing it in cooperation with Sandia and the University of California, Berkeley were part of the original team. Berkeley because they were doing molten salts as fusion blanket cooling mechanisms. Hybrid, pulling. That reactor was designed or was conceived of by pulling technologies from other places. With any new reactor, the problem can, in the end, be reduced to one of materials. Can you get the materials to make it hold together? Turns out that for the gas reactor and for this molten salt reactor, the spectrum is sufficiently hard, it's an epithermal, not a thermal spectrum, that you can imagine, under the right conditions, doing deep burn in it. Although not burning as much as you can in a fast reactor, maybe burning enough so you can get the vast majority of the actinides burnt away and have a direct disposal fuel pool. So these are concepts. I'm not trying to tell you that we have the answer in our back pockets. This is UGRAF reactors, not real reactors. But it has enough promise to be really, really interesting. And DOE, most folks, you don't have any wood anymore, touch wood, will fund a small study this year, basically a feasibility study, sort of like a ho-ho test. Is there something obvious that we missed? And I've done a cursory study of it, and I've had smart people do more detailed studies, and I think it can work. So, low pressure, basically gas reactor fuel, fast reactor technology for the heat removal systems, no delta P problem out to the hydrogen plant, passive safety. What can be wrong with this? So, we're going to focus on our strengths. That's always a good tactic. If ever when you grow up, get into the strategy business, figure out what you're good at and do it is usually lesson one. So, gas reactors, thermal neutron reactors, and AHDR including that, fuel cycle and associated technologies still will be the future. We have to rebuild Oak Ridge and in that domain, and it won't be done by classic aqueous separations. We may use aqueous techniques, but they'll have to be co-processing, where we pull plutonium and other actinides together, neptunium, others, because this country will never, in my opinion, go support a fuel cycle that's based on separation of pure plutonium. It's just politically impossible for this country, as far as I can foresee. As people who, in my division, David and Belmore know, I very strongly support the education programs. This summer we increased the number of students we've got, and I set up a series of seminars over the summer. I think there are about half a dozen. David gave one. What was yours on, David? Separations. We did one on space power and so on. Just 6 example seminars. I want students to come to Oak Ridge and spend summers there. I want them to learn while they're there, and I want them to come back as employees. Because, I did a quick study of my division, and to keep my division at the same staffing level, I have to hire a person a month. Because the division looks like the first 2 rows here. All right, so this is self-interest. Yeah. Who's he speaking about? You, Mario, right? So this is very important to us. Is engaging with you, the academic community, the students, offering opportunities to come and do work with us, get interested in the things we're interested in the future of nuclear power. There's a lot going to happen over the next 50 years. Why not? The next 20 years, and it won't be me, it won't be these guys, it'll be you guys that'll do it, because nobody else is going to do it. So, I think that's the last one. Oh no, there we go. This is important. As I've tried to convince you, the U.S. has been making hesitant steps towards active consideration of the post-fuel cycle. DOE and the national labs continue to pursue that goal. The national labs have been extremely active in doing this. But here is the kicker. The guys who were around in the 70s are still there. And they're starting to figure it out. My friend Tom Cochran is publishing material saying that this country has started reprocessing again and is evil. There was a piece on NPR on the fuel cycle program 2 Thursdays ago or a Thursday ago. You can probably still click on the website and get the audio stream. The people who opposed had reprocessing essentially eliminated in this country because of the concerns of plutonium are starting to figure out that we've made some steps forward and are turning their attention to us. And I can't predict what will happen with that. I believe we've done enough to fight them off, but it's going to require clarity of message, passion, and good science. Thank you. Okay.
We have time for maybe 1 or 2 questions. Okay, Don.
I thought that was an outstanding presentation. Incidentally, I would probably be in the rows in front of this too.
So we had to average a little.
But I talked to a spectrum of retired nuclear people about new power plants, and to the man they all said the U.S. does not have the capacity to construct a nuclear power plant. This was mentioned to a CEO of a large French organization, and his response was, how could the U.S. allow that to happen? I noticed you almost touched on that subject just briefly on the vendor, but I think that's a significant item that in general the national labs really don't pay much attention to.
You're exactly right. Obviously, how could the U.S. allow that to happen? It's the U.S.'s way to allow that to happen. If there isn't a market for something, the people move to other jobs. Westinghouse is owned by British Nuclear Fuel. The old B&W and CE previously joined Westinghouse. The old B&W operation is owned by Framatome / Siemens or whatever. But I'm not overly GE still can build reactors and do so successfully in Japan. I'm not overly concerned about that because building a reactor in the end, a conventional or advanced light water reactor is a market decision. And if somebody else, Japanese, can build it cheaper, then they will. I'm much more concerned on the R&D side. It's difficult. I mean, what you're seeing, countries like France, European countries and Japan, have a different social structure, which reflects itself in this structure. They perceive supply of energy as a national need, and their companies or groups of companies are nationally owned. French is the best example. The French government actually owns, by a complex interrelationship through a holding company called Areva, CEA, the research arm, Framatome, and Kojima. And in fact, CEA owns itself because CEA holds 90% of the shares of Areva on behalf of the French government. So CEA owns, which is the equivalent of the national labs, owns Framatome and Kojima, in turn fund research at CEA. But if you've got no hydrocarbons, and you're in a country that's come out of a war where you're invaded, in 1945, 1930, 40, 1914, you see, security, national security, is key to your existence, and you can't afford to leave it to the forces of the market. In this country, we've taken a different view, for better or worse, left it entirely as a market force, which has allowed the construction industry to wither away. It is just a fact. I don't perceive it as good or bad, is what I mean. I can't control it anyway. Yes, Bob.
You spent a lot of time on the international issues of nuclear power, and other than the French, Europeans have this sort of love-hate relationship with nuclear power, depending on the country, how much love and how much hate. But yet they're probably more committed to CO2 reduction than the U.S. Do you see the Europeans coming around on nuclear power and sort of embracing it, at least in the blue side? And B, how important do you think how important is international agreement on nuclear power for us to make much progress in this country? I mean, this international...
I understand the question. Let me deal with the first one. The answer is not uniform. The British government at the start of the year issued a study on the future of energy for the UK, where basically they're going to renew their way out of the Kyoto Accord. They kept nuclear on the table, but as the last resort, basically. They said we need to have the capability, but we'd rather not use it. France, of course, will be strongly pro-nuclear. Germany is still going with the red-green, or now the red, I guess just red alone, government is still phasing out nuclear. Sweden has closed a power plant. Finland is building a power plant. Why is Finland building a power plant? So it can export electricity to Sweden. Nuclear power plant, I should add. The community as a whole, that is to say in Brussels, when the EC debates these things, the environmentalists have control, and nuclear has a tough time. So, heterogeneous will take time, but again, I think, to part of your first question, needs of France, a very large country, and other countries will be sufficient to keep nuclear on the table. Will they embrace it as Europe as a whole? No. How important is it? I believe it's crucially important. I mean, the previous question has shown that the offshore flight of construction, nuclear inevitably is an international business. The material is fungible, it moves. It's hard to imagine how you get from here to there, but I think ultimately we'll end up in a state where a large part of the power in the world is provided by fusion or something like that, but in an internationally controlled way, in energy parks or something, where you can isolate both production and deal with the waste as is. Although I must admit I can't imagine the social structures or the pathway that will get us there at this point, but fortunately I don't have to solve that problem today. And what I need to do is have active and meaningful research programs in this country so we can engage in a dialogue. It's our ticket to entry. If we don't do that R&D, what right do we have to preach, which is what 20 years we've done? We have to have the R&D. We have to talk from a position of strength and knowledge and not just from a fundamental text.
We have a question from our cyber audience. This is from Dr. Madeline Feltis, who's with DOE. Please describe for the crew the new Ornell gas reactor fuel laboratory facilities that are being used for the HER program and the Cristo Fuels work at ASTF. Okay, Dave?
Okay, Madeline, thanks for the question. I didn't want to go into details of programs. I was taking a high level, but since you asked, DOE is making a significant investment in recreating and extending gas reactor fuel technology down at Oak Ridge in cooperation with Idaho National Lab. We are working on production of kernels, on coating, and there is DOE investment into the fundamental technology. This is the core fuel technology that is described as the AGR, Advanced Gas Reactor Program, but it's the core fuel technology that will support VHTR, which is DOE's research reactor, and ultimately we believe will support AHTR. Part of the issues associated with gas reactor fuel, which are tiny little particles, is characterization and quality control, and we're putting together a compacting lab to look at forming the compacts and characterization. Beyond that, I don't have the details with me, and I can't give a more detailed answer than that, but if you would contact Madeline Feltus at hq.doe.gov, madeline.feltus, or contact me directly. I can give you more information if you're interested. Thanks.
Okay. I think we better call it adjourned and downstairs. We do have refreshments downstairs. Dr. Hill will be downstairs to answer more questions. But before we go downstairs, and I should remind that everybody's invited, let's express our appreciation again to Dave for his
They got Mary Wood going tomorrow.
well,